All right, here we go. So I am very happy to be talking to you here because Jan and I get the envious role of being Father Christmas in this conference, in that we get to actually show you the real deal. You know, so far you've heard lots of people telling you lots of nice things about programming languages and theory and all this stuff, but at this point maybe it's all vaporware. You don't know. And I'm here to tell you that it is not vaporware. And also to do something extremely dangerous, which is tell you lot how to actually do something. And more than that, we're actually going to do some of that live in front of you. And this is the point at which I'm struck down by the god of demos for my hubris. But let's see how far we get before the lightning strikes. So today, what we're going to talk to you about is the Plutus Playground. And the point of the Plutus Playground is, well, why are we here? What is the point of this conference, all of this infrastructure that we're building up? Well, at the end of the day, we want to actually write some smart contracts. We want to do something with this system that we've been building. And the Plutus Playground is here to help you do exactly that. So it's an environment for writing and testing smart contracts in your browser. You don't have to install any fiddly dependencies unless you want to, so it's a bit like Remix if you in the Ethereum world, if you've seen that, and that's what we're going to be showing you today. And you can go all the way up to actually testing your contracts and seeing that they actually do what you expect them to do. Just send all the money to my account. I should really put that in as a backdoor. So first of all, I'm just going to do a little bit of a retread of some of the ground that Manuel has so adeptly covered, just to make sure that we're all on the same page here with what's going on, because this is really the pedal hitting the metal. So we need to know what we're doing. So to revise a little bit, the anatomy of a smart contract. You've heard people say on-chain, off-chain over and over again. I'm going to say it again. We have some code that runs off the chain. It runs in the user's wallet, typically. This is what they interact with. It's what listens to them saying, I want to send all my money to the Fuzzy Bunny Kittens crowdfunding campaign, and then submits a transaction that actually does that. And then there's the on-chain code, which is what actually lives in the transaction. It runs during transaction validation. It makes sure that nobody steals all the money. That's very important. But these two pieces of code, as Manuel has explained, are very tightly coupled. They need to understand each other, they need to cooperate, they need to exchange data between each other, and they jolly well better do that in the same format, otherwise we're going to drop everything on the floor and everybody's going to be sad and all the money is going to be gone. So the goal of the Plutus platform is to bring these things much closer together, so you can write your on-chain code and your off-chain code in the same language, and that language is Haskell, and even in the same file. And more than that, you can actually really reuse the same types between the two. So you can just, the same data structures, the same definitions, and maybe if you're not a Haskell developer, you don't feel that deep inner feeling of joy that sentence engenders in me. But I promise you, this is the thing you want. This is the thing that will make your life easier. The types are definitely your friend, and you want to share them as much as you can. Moreover, the library and toolchain support that we have built allows you to write exactly the same code to define a contract and run it on both Cardano, obviously, because that's where the real stuff happens, but also on the Plutus Playground, which I'm going to show you today, and also on a local emulator, which we affectionately call the mock chain. And that's what's actually powering the Plutus Playground under the scenes. But crucially, you don't have to jump through horrible, awkward hoops to do testing. It's all just the same nice interface. So let's drill a little bit further down into the anatomy of what's going on. So we're going to continue our color coding adventure. We have this blob of off-chain code written in Haskell that lives inside the user's wallet, and then, as Manuel has shown you, you have these fancy, well, the previously blue-colored, now purple-colored blocks that live in those quotation blocks that actually are going to turn into on-chain code, which are also written in Haskell, or as we like to call it, Plutus TX, because it's not quite Haskell, but pretty much Haskell. And these are what actually define the logic of your transaction most of the time. So that's where, as you saw in the crowdfunding campaign, check that you got enough money, check that the deadline is passed, yes, okay, no, not okay. That's where that's happening. And And so that's the second stage, the first stage being the Haskell, the second stage being the Plutus TX. But in addition to that, we want to make it easy for you to come across these boundaries. We don't want these stages to be awkward, rigid things that you keep butting up against as a programmer. And in particular, you often want to parameterize your contracts. You don't always want to pay Jim 10 ADA, sometimes you want to pay Jane 10 ADA. You want to actually be able to parameterize them. And so we make it easy for you to lift chunks of data from the Haskell world at runtime in your off-chain code into the on-chain world seamlessly. And so that will all just work. And this is one of these things that hopefully when we actually get to look at it, you might not even notice that it's interesting. That's the goal, is that it should seem really easy, even though there's actually some work going on behind the scenes. And then this all then gets turned into a transaction that actually goes on the chain. And we're going to see all of these pieces shortly. I then also want to say a little bit more about what Manuel described earlier, where he explained about the extended UTXO model and how validation works. So just as a reminder, how do we check whether we can spend a transaction output? Well, the spent transaction output has to accept the spending transaction by and we do that by taking its validator and just feeding it a bunch of bits of information. And if it evaluates successfully, then it's fine. If it doesn't, then the transaction is rejected. And this is done by the slot leader. And in addition, if you don't know what that means, it's the person who actually runs all the code. It's part of the Ouroboros protocol. The way that works is that, well, we're writing in a functional language. This validator script is just a function, and it just takes these things as arguments. And that's exactly the pattern that we will see literally in the code in a moment. So remember that. That's going to happen. In addition, Manuel denoted this with a little sigma. There's some additional information about the current transaction that goes in as well. Says things like what block height are we at, i.e. like what time is it, and some other pieces of information. And crucially, this actually uses exactly the same mechanism for lifting data into on-chain code as you can do locally. And you can also then use the same types. So not only can we share our types between our on-chain code and our off-chain code, we can share our types with what happens at validation time with the slot leaders, and we can be sure that everything is just going to work and we don't need to worry about accidentally screwing it all up when we do it ourselves. And so, to summarize, there are kind of 4 interactions that we need to remember and bear in mind. And conveniently, these correspond exactly to the 4 Haskell modules that you would import when you're doing this for real. And again, in a moment, you will see precisely these things in action. So the first thing that we need to remember is that the off-chain code talks to the wallet. This is to do things like ask for your public key, submit a transaction, register that you want a trigger to take an action on some later date. These are things that the wallet is going to do for you, and you need to say, please do this. That lives in, unsurprisingly, the wallet module. The off-chain code also needs to actually make the transactions. That in order to do something, you have to make a transaction so you can submit it onto the blockchain and actually have something happen. And all of this material is handled by the ledger module, which talks about things that go on the ledger. Thirdly, we have this staging business whereby we write this Plutus TX code that gets turned into Plutus core code that goes on the blockchain. There's some stuff to do with that. Unsurprisingly, lives in the Plutus TX module. And finally, there's the types and structures that are used during validation that you will want to care about when you're writing validators, and those live in the validation module. So just remember that those are the kind of the four things that are going on that you might care about, and we'll see those in a moment. So I'm now going to actually show you some code in Emacs. Where else? The font size on this is not ideal. Oh dear. Is it possible to turn this off? If I just take it out of the socket. Nobody saw that. We'll put it back later, I'm sure it's fine. So this is a Haskell file. Hooray, Haskell. If you haven't seen Haskell before, this is not going to be a Haskell tutorial, but hopefully it will not be too bewildering. And so there's a little bit of stuff at the beginning, which we're not going to worry too much about now. I suppose can I move this a bit? There we go. We do see that here I have written 4 imports corresponding to the 4 things I just told you about. As a reminder, Plutus TX is about stage code and writing things that run on the chain. Wallet is about talking to the wallet. Ledger is about making transactions. validation is about things that happen at validation time. So there they are. That's exactly what you'd write yourself. So I'm now going to pop the hood a little bit and show you what's really going on here. And the reason I'm going to do this is because although it's unlikely that you're actually going to care about the Plutus core and what's going on, it is interesting to know what the sort of assembly language of what you're doing looks like. It's sort of going to prove to you that there really is something there. You might have no idea what it means, but it exists. I'm not just making this up. It's not, these functions are not implemented. These functions are in fact implemented. They don't just like return the empty string all the time. So here is the simplest example I could come up with of using Plutus TX. So we're going to write the +1 function as a function that would run on the chain, adding 1 to an integer. And well, what is that going to look like? Well, it's going to be an opaque blob of code as far as the off-chain code is concerned. The off-chain code it's just once you've made it, you can't really do much with it. It's going to get run later, but that's what it looks like. And here we see the funny quotes, the funny dollars and brackets that Manuel was talking about before. So for the lispers around you, this is going to be old hat. But for the rest of us, let's take a moment to think about what's happening. And what's happening is that between these funny double bar brackets, we have a Haskell program. And what that program does, I'm going to reformat it so that it fits on the screen, it's a function that takes an integer and adds 1 to the integer. Very exciting. And what these little quote brackets do is give you a representation of that Haskell program, which is what we're then going to compile. So that's all this is. This is just, you can just think of this as the program that's inside the brackets. And then we feed it to the Plutus tx.compile function, which surprisingly compiles it. And then finally we feed it into these double dollars, which takes us back into the real world and out of the quotation world, and actually shoves the compiled program into your program to use it. Now, what that actually means is we end up with a Plutus core program. So let's look at it. Oh, there it is. Oh, I know what it needs to do. Rotate it like that. So this is a genuine Plutus core program that you could put on the blockchain. Ooh. And we can see a few interesting things about that. It has a version. That's interesting. So this is actually something that we do to make sure that when things change, we know exactly what version of the language is being used, so we don't do the wrong thing. You can see a bunch of incomprehensible nonsense, but what I'm going to tell you is that this bit here corresponds to the bit that we wrote, and the rest of it is not so interesting at the moment. And if we squint, we can see that this is a lambda function, so like a function, which is going to take some incomprehensibly named variable, which is, I promise you this is an integer, and is going to, I promise you this is calling add integer, add, and this is 1, is going to add 1 to it. So at the end of the day, Plutus core is not that dissimilar from Haskell in many ways. And so actually a lot of what's going on under the hood here is not so clever. There is some cleverness, more cleverness that we'll talk a bit about later, but it's comprehensible. We're just one of the virtues of the approach that we've taken is that we actually are quite close to how Haskell represents things. So now this would not be terribly useful if we were only able to use integers. I mean, you can do a lot with integers, but not everything. And in fact, we can just use pretty much all of the Haskell data types that we would want to. So here's a very simple example where we use the type maybe, which is in the Haskell prelude and just is either a thing that's either there or not there. So it's like an integer or nothing. And this does a pattern match on it. And in the case that there's something there, it gives you the thing. In the case that there's nothing there, it gives you 0. So it's give me this thing or else 0. And this will just work. Hooray! You can reuse your data types. Things will just work. You can write your own data types, and things will just work. It's not all special built in. It's just whatever you want to write. And I won't show you that because that's a bit longer and even more incomprehensible. What I will show you is here is a ever so slightly more real program. So this is actually part of the example that Jan is going to show you in a second. This is a real validator script for a simple guessing game. And so this has a couple of user-defined data types, a couple of bits of magic to make sure that you can do that lifting that we talked about earlier. And then it's just a function. And well, what do validators look like? Well, they're functions that take a redeemer, the data, the validation info, just like Manuel said, nothing fancy here, it's exactly the same, and then it does some computation and decides whether or not it's going to accept it. And this, it's simple but significantly more complex program is also, what do I call it, is also, oh, it's very long, it's not that long, but it's quite long for an Emacs terminal. But it's a real program that we can write and that works and that you can actually execute using the Plutus Core Evaluator for real in the Plutus playgrounds, and it will actually evaluate and do what you want it to do. And I'm now going to hand over to Jan, who's going to show you how to use these things in anger and actually see something that isn't gibberish.
Okay, thanks. So this is the Plutus playground. There are no slides here. I'm just doing it all live in the web app. So this is actually working. And you can try it out for yourself later. When you open it, the first thing you'll see is the code editor, and that's this field where we're going to write the smart contract. And it comes preloaded with a number of examples. So we have the crowdfunding campaign, a game, one example that just produces different log and error messages, and a vesting scheme. And we will look at those in a minute. I just want to show you the rest of the user interface first. So we have the contract, we click compile, and that brings us to the second part of the playground. And this is where we can set up a simulation on the blockchain that uses this contract. So we can set up a number of wallets. Each wallet has an initial distribution of funds, so 10 ADA in this case. And these wallets can perform actions. And these actions, they're going to be defined in the contract that we will write. And because we have an empty contract here, there's only one action that they can do, and that is pay something to a public key owned by another wallet. So let's try that. Let's pay 8 to the second wallet. The public key of the wallet in the playground is just the number of the wallet. And then wallet 2 pays back 8 to wallet 1. And we can put up any number of actions in the sequence here, and then the emulator will run it against the mock chain. Oops, sorry. 1. So now we get to the third part of the playground, and that's where we see the results of the simulation. I'm zooming out a little just so that we can see this whole graph here. And this graph shows the entire blockchain that has been generated. And the time in this graph flows from top to bottom. So the node at the top here, that's the initial transaction, and the other nodes are the remaining transactions, and the node at the bottom here, this UTXO node, that's an unspent output. So the last ones at the end, they're always unspent outputs, and all the other nodes are transactions. And the edges in this graph, they're pairs of input-output connections. So one transaction consumes the output of the previous transaction. And the size of this edge shows you how much ADA was transferred in that. So we can see here, each wallet got 10 ADA initially, and wallet 2 received 8 ADA from wallet 1, and wallet 1 received 8 ADA from wallet 2. The second part of the output is this log that we'll see here, and that just lists all the events that happened in the simulation. So we see transactions that were valid, transactions that were rejected, any script failures, log messages from the wallets, and we get quite a lot of information from this. And here we see 3 transactions, the initial one and then the 2 that I just created. And the final output that we get is the balances of the wallets at the end. So each wallet is back to 10 ADA that it started with. So this is the general workflow of the playground. We write something, we set up the simulation, and then we look at the results. to make sure that the contract behaved exactly like we wanted it to. Now this is the full source code for this game that we already saw the validator of earlier in Michael's talk. I'm just going to make it a bit bigger. Okay. So we start out with the module name, can be anything. Then we have the imports that we need, as before. So we have PlutusTX, the prelude with some helpful functions, ledger, validation, and wallet imports. And when we're working in the playground, we also need to import the playground.contract module, because that lets us define the contract endpoints that the wallets are going to use to create transactions with this endpoint. And then in this line we also have another Haskell library that we're importing from ByteString that we only need in this particular contract. So we can use any other a lot of other Haskell libraries in here as well. Now we need to define the data types that we want in this game. So the rules of the game are the first player makes up a secret word and puts the hash of that word on the chain. So they're using a transaction output that's locked by the hash of the word, basically. And the second player has to guess the word, and if they guess it right, they get the funds in that. And to encode the hashed word, we just have this hashed string data type. And for any data type that we want to convert to the on-chain representation, we need to call PlutusTX.makeLift. That's why we have that here. And then there's a helper function that lets us take a Haskell string and produce the data script for the transaction. And in this, that's where so first we have the hashed word here using the SHA-2 function, and we embed that into the data script using ledger.lifted. And ledger.lifted takes anything that you have defined makelift on and puts that into the on-chain representation. So we need that for the data script, and then a similar definition for what goes into the redeemer script, and that's the guess of the other player. And here we have a clear string, which is also going to be the byte string on the chain. And by using these types that we've defined, we can make sure that in the validator script we don't compare two wrong things. So we don't compare a clear string and what was it called? A clear string and a hash string, but we always compare two hash strings, for example. So we have the clear string. We can construct redeemer scripts containing the clear string with the make redeemer script function. And then finally, this is the validator. This encodes the game logic. So we have the two quotation marks from earlier here and here, line 42. And anything in between that this is the actual on-chain code, all written in Haskell again. And in here, we can use the import p dot from earlier. So because we imported the prelude qualified as p, then we can use any functions that are defined in there with the splicing operator. These are the $2. So that lets us use functions that were defined outside of this script and puts them into the script. So we compare the two byte strings. If they match, then we just terminate, or we just return the unit value, no error. But if there's a mismatch, then we produce an error using the error function and a little log message so that we know what happened. Now we have the on-chain code. We need to define the contract endpoints now. So how do the wallets interact with the game? And that's what the next few functions here are for. First, the first interaction that we need is locking some funds with a secret word. This is what the first player is going to do. So we have a function that takes two arguments, a string and the value, and it returns a value of type mock_wallet. And mock_wallet says that in this function we can use the wallet API to produce transactions and to interact with the blockchain. So we're using the wallet API as an intermediary to talk to the chain. And pay to script here, that's one of the functions from the wallet API. And we're just paying the value to the address of the script using our make data script function from above. Now the second endpoint that we need is guess, which takes the guess and also returns a mock wallet function, because here we're using collect from script, which instructs the wallet to take out all the unspent transaction outputs at the script address using the validator and the redeemer scripts here. Now there's a little problem with this at the moment, because to collect all the outputs at the script address, the wallet needs to know that this is an interesting address so that it can watch this address for any outputs that are produced to it. Otherwise it doesn't, because it can't just watch all the addresses of the entire chain all the time. And to make the wallet aware that this is an interesting address, we have a third endpoint which is called start game, and it just tells the wallet to start watching the game address. At the end of the contract, we have 3 calls to make function, and that's what will generate the contract endpoints that we're going to see. So make function lock, make function guess, and start game. And we can call make function on any function that has this structure that returns the mock wallet. So let's compile it. And now you can see that the wallets have learned how to do these actions. They can lock something, they can make a guess, and they can start the game. So wallet 2 has to start the game. Wallet 1 will lock the funds, and then wallet 2 will make a guess. Let's see how that works. 8. Wallet 2. Let's click evaluate. Okay, so here we have the transaction from wallet 1 locking the 8 ADA, and then this is wallet 2 retrieving them because the guess was correct. And that little bit here, that's the change that goes back to wallet 1. And in the log we can see there were the successful transactions, as you would expect, and wallet 2 ends up with 18 ADA. If you put in the wrong guess, now there's no transaction that spends this output, and we can see in the log that the validation failed for this transaction. So that's something that you can only get in the playground and in the emulator. So you get these error messages and detailed reasons why validation failed. You won't get that on the real chain, but it's very useful for designing and debugging contracts. And now wallet 2 only has 10 ADA, wallet 1 2 ADA, and the remaining 8 ADA that are missing, they're still locked in the script output. Let's look at the crowdfunding contract now. I just want to show you these blockchain triggers in a little bit more detail that Manuel mentioned earlier. So we've this is the contract endpoint that makes the contribution to the campaign, and once we've made the contribution, we register this refund trigger, and that's a condition on the blockchain that becomes true at some point. So in this case, it means the campaign the deadline for the campaign has passed, and the funds haven't been collected yet. So in that case, the contributor is entitled to a refund. When that happens, it calls the refund handler. So this is like an event-based system where you have some conditions, and then you can call an event handler that deals with, or that reacts to this condition. In this case, the refund handler is implemented here. And there's one important difference between this refund handler and the guessing endpoint that we had in the game earlier. Because earlier we were using just collect from script from the wallet API, and here we're using collect from script transaction because we don't want to try to reclaim all of the contributions to the address, but only the one that we made ourselves in the initial transaction. And that's why we're calling collect from script TXN to only claim back our own contribution. If we try to collect all the other ones, then the transaction would be invalid and we wouldn't get anything back. So we have to make sure to create a valid transaction. And this whole blockchain trigger system, that all runs in the client code. So it doesn't go on the chain. This is done by the wallets themselves. So we're going to run a little campaign, 2 contributors, and one is the campaign owner, and they have to call schedule collection again so that they start watching the address. And zoom out. And you can see here that it generates the correct form for the data types that you want to put in. So we have defined a campaign data type above, and the playground automatically gives us these inputs here to put in the blockchain height, the values, and anything that we need. So let's say the campaign runs to 10 blocks, target 15 ADA, collection deadline 20, and the owner of the campaign is this public key. Let's make 2 contributions. And we have to make sure to put in exactly the same details because the campaign, this definition is part of the address of the script, and if we put in a different number here, for example, then the contribution will go to a different address and it won't be registered as part of the campaign. So 15, 20, owner is 1, and then let's contribute 8. And now we have to add a wait action again, because if we run this, then we won't be at 10 blocks. So the campaign owner won't even attempt to collect the funds yet. So we can use this button here, add wait action, to add a number of empty blocks to the chain, just to simulate the passing of time. Now this is a bit more complex. But you can see these are the 2 contributions, 9 ADA and 8 ADA, and this is Wallet 1 collecting the funds. And now if you look at the logs, we also see these messages from the wallets. So in the wallet API, we can also log some information here. And then at wallet, at block height 10, this is when the collect funds trigger fired and collected the 2 contributions. And what happens if we have an unsuccessful campaign? Say wallet 3 only contributes 2 ADA, and we have to add some more blocks. So we have to get past the campaign collection deadline, 20 blocks. Now you can see that the contributions here were claimed back by the original contributors. So message from wallet 2 claiming refund, message from wallet 3 claiming refund, and everybody's back to the balance that they started with. So we can use the playground to go through really complex interactions with our contracts, and it all evaluates quite fast considering what it's doing, because when you click evaluate, it really spins all the wheels. It compiles the contract, emulates the transactions, it runs the compiled code and returns all the results to the web interface. That's all I wanted to show for the demo. There are some links here to more documentation. The URL of the playground is here, so you can try out these examples yourselves. And there's a Docker image as well if you want to download it and run it locally. And I encourage you to try it out, make some changes, see how the contracts behave. Thank you.